So let us discuss the properties of Fourier transform in Unit 2, Fourier series and Fourier transform. So let us see these properties one by one, very simple properties. Number 1, linearity. Let us see what is this property linearity. If x1 of t's Fourier transform is say x1 of omega and x2 of t's Fourier transform is say x2 of omega, then what is linearity property? As you know that from linearly adding these two signals, that is a into x1 of t plus b into x2 of t, where a and b are constants, Fourier transform is, so what is a into x1 of omega plus b into x2 of omega, where a and b are constants. Very simple to prove this linearity property. Solution. What we want to find out? We want to find out Fourier transform of this function. So just substitute in the definition. The Fourier transform of a into x1 of t plus b into x2 of t. So what we have to do? We have to just substitute this function in the definition of Fourier transform, that is a into x1 of t plus b into x2 of t. Just substitute. What is the transformation? The transformation is e power minus j omega t dt. So let us separate the integrations to each term. So therefore we can write this as a as a constant, I said. So minus infinity to infinity x1 of t into e power minus j omega t dt plus b into integral minus infinity to infinity x2 of t into e power minus j omega t dt. So which can be written as a into, so what is this? This is the Fourier transform of x1 of t. The answer will come in omega. So therefore x1 of omega plus b into, this is the Fourier transform definition of x2 of t, which is given as x2 of omega. So therefore what we can write? Therefore a into x1 of t plus b into x2 of t's Fourier transform is, what is the answer? A into x1 of omega plus b into x2 of omega. So this is the answer. So let us see the analogous exponential Fourier series. If x1 of t's periodic signal Fourier series coefficients are Cn, x2 of t's Fourier series coefficients are Dn, then ax1 of t plus bx2 of t's exponential Fourier series coefficients are acn plus bdn. So that is the property we have discussed in exponential Fourier series. So now let us discuss the second property. Let us discuss the second property, time shifting property. Time shifting property. All these properties are very, very important for competitive exams. So what we write? Time shifting property. If x of t's signal Fourier transform is say x of omega, then what we have to do? Time shift x of t, that is x of t minus t naught Fourier transform is, here minus is there, minus e power minus j omega t naught into x of omega. So this is the, if plus is there, we have to take plus. In time shifting, if minus is there, you have to keep minus. If plus is there, you have to keep plus. Remember that hint. Okay. Now, so proof, very simple proof, just substituting in the definition. What we want to find out? We want to find out the Fourier transform of x of t minus t naught. X of t minus t naught. So let us substitute in the definition. So that is x of t minus t naught into e power minus j omega t dt. So let us substitute in this integral. Let t minus t naught is equal to tau. So if we substitute t is equal to minus infinity, tau will become minus infinity. If you substitute t is equal to infinity, tau will become infinity. So what is differentiation? dt is equal to d tau. So let us substitute these things in the above integral. So therefore the above integral is written as, the limits will not change, minus infinity to plus infinity, x of tau e power minus j omega into t can be written as t naught plus tau into d tau. So in this integral, what is the constant? The constant is, so e power minus j omega t naught is a constant because this integration is with respect to tau. So this term is constant in this integration. So therefore take it outside. Integral minus infinity to infinity x of tau into e power minus j omega tau d tau. So what is this? This is the definition of Fourier transform of x of t or x of tau. So whatever it may be, the answer will come in omega. So therefore it can be written as e power minus j omega t naught into x of omega. So therefore we can write it as, therefore x of t minus t naught's Fourier transform is, what is the very simple formula? E power minus j omega t naught into x of omega. Similarly, if you plus is taken, similarly x of t plus t naught Fourier transform, similarly we can also prove that, so e power plus j omega t naught into x of omega. So remember that very simple hint, if x of t is exponential Fourier series coefficients are Cn, what is x of t minus t naught? Exponential Fourier series coefficients e power minus j n omega naught into j omega naught t naught into Cn. So both are same, you can check that. Here just replace n omega naught is the discrete spectrum. Discrete spectrum is replaced by omega. Cn is replaced by x of omega. So therefore I said earlier, exponential Fourier series and Fourier transform both are same. Exponential Fourier series will give discrete spectrum, whereas Fourier transform will give continuous spectrum. Just if you substitute in place of omega, n omega naught x of omega by Cn, so that will be the exponential Fourier series coefficients of x of t minus t naught. Okay. Now let us see the third property. So let us see the third property, frequency shifting property. Frequency shifting property. This property we have not discussed in exponential Fourier series. Frequency shifting property, and a very simple property, frequency shifting property. Let us see this. If x of t is exponential, Fourier transform is x of omega, then if you multiply x of t with any, say e power j omega t term, x of t, I am multiplying with, as the name itself indicates. So if you multiply x of t with high frequency term, remember that omega 0 is the frequency, high frequency term, that means frequency term, e power j omega 0, as you know that this is the complex exponential signal oscillating with the frequency omega naught. If you multiply, so then the spectrum x of omega minus omega naught will come. If plus is there, you have to take minus. If minus is there, you have to take plus in frequency shifting operation. That is the hint you have to remember. Now let us prove this very simple property. Proof. What we want to find out? We want to find out the Fourier transform of this. So therefore the Fourier transform of e power j omega naught t into x of t, what we have to do? We have to just substitute in the definition, infinity to minus infinity to infinity, e power j omega naught t into x of t into e power j omega minus j omega t dt. So what we take? Integral minus infinity to infinity x of t into e power minus j omega minus omega naught into t into dt. So you can see that if omega is there, you have to write the entire function will come in omega. If in place of omega, what is the function we have? Omega minus omega naught. If you find out the answer will come as a function of x of omega minus omega naught. So therefore from this, what you can write? E power j omega naught t into x of t's Fourier transform is x of omega minus omega naught. In frequency shifting operation, remember that if plus is there, you have to take minus. If minus is there, you have to take plus. Similarly, what you can write? Similarly, if complex exponential signal e power minus j omega 0 t is multiplied with x of t, so then the frequency is, why this is called as shifting? Let us see why this is called as shifting. I will explain. So this is the property, frequency shifting property. For example, I will show the example for this. For example, say x of t is a signal, a periodic signal, let us say, of any arbitrary shape. Let us take any arbitrary shape. X of t is any arbitrary signal. So what it will give? For example, if you find out the Fourier transform of this signal, for example, say if you plot the Fourier spectrum, so the spectrum almost will come like this. We have seen in different problems. Just say the spectrum will come like this. So what I am doing is that I am multiplying this signal with high frequency term with frequency omega 0 t. So what will happen? Let us see. This is the original information of the signal. The signal will shift to a location. The signal will shift to a location. What is x of omega minus omega naught? From the observation x of omega minus omega naught as time shifting property, same x of omega is shifted to omega naught, as we have seen in time shifting operation. So therefore, the same spectrum is shifted to a frequency omega 0. The same spectrum, because of this multiplication, the same spectrum is moved to some other location with central frequency omega naught. Suppose if you multiply with the same signal with high frequency term, say e power minus j omega 0 t, what is x of omega plus omega naught means? The same spectrum is shifted to left side. So that's why this operation is called as frequency shifting operation. So this is what the important point you have to observe from this frequency shifting property. So this is about the first three properties: linearity property, time shifting property, and frequency shifting property. Thank you.